Now that we have this idea of absolute convergence behind us, that's really an interesting topic in its own right, but we really use it as a way to uh, leverage ourselves so we're in position to talk about the ratio test and then the root test as well. Here's the ratio test, pretty cool one. I find that when I was a student, I found that I really liked the ratio test. Pretty powerful test. You can really tackle some interesting series and not overly complicated. And I find a lot of students over the years they like the ratio test also. So here we go for the series from 1 to infinity an. We're going to investigate this limit. It's the ratio of the a n plus 1th term to the a sub nth term. So whatever a sub n is, we'll just take that as the nth term there. We'll copy it as a denominator. In the numerator, well, we'll take the next term up. So and we'll look at how we can do that. Well, actually, we've done it in the past, right? Even with alternating series. Okay, anyway, we'll take a look at that ratio, the limit of that ratio. And you notice we're even taking an absolute value. So we turn everything positive in just as part of this test, and we find out what the answer is. Now, maybe L is a number, maybe it's 0 or infinity, right? If L is less than 1, and we know it's going to be positive, so really if it's between 0 and 1, then it converges absolutely. Boom. Really nice way to show absolute convergence there with that limit. If you get something bigger than 1, then it diverges. And kind of the secret option number 3 that nobody likes, if that limit turns out to equal 1, then we don't know. So just really quick, why is this the case? Um, and we're really thinking like, do the terms increase or decrease? If the limit is less than 1, that means the terms are getting smaller. And so if that ratio in the end is something less than 1, the terms are getting smaller and it converges. And there's more going on than that, but I think that'll do for an explanation. If the ratio is getting larger, it's bigger than 1, then the terms are increasing, and it's maybe not hard to argue that it diverges. If it equals 1, then the terms are not changing, and you might say, well, then it diverges, right? But that's turns out that's not necessarily true. It We don't know at that point, so then it's inconclusive. Okay, really convenient test. Let's take a look at it with this problem here. Again, we're back to just the simple converge or diverge, although if it converges absolutely, then we'll go ahead and say that in the answer. But the question, we're just going to keep it the simple form, converge or diverge. Okay, here we go. N equals 0 to infinity, 3 to the n over n factorial. Okay. Now, obviously, we're going to use a ratio test, and I will even, in the next section, we'll talk about how we can identify what test to use in any given situation now that we've learned so many. But okay, for this one, we know we're going to use ratio. So what are different parts, right? So, well, an, we're just going to copy it. What's an plus 1? Well, we've said it before. An plus 1, take your n, both your n's, and replace them with n plus 1. That's all you got to do. The n plus 1 term. Okay, so now we're going to investigate, and see my first line here even, but that's all right. We're going to investigate the limit of this one divided by this one. Okay. Now, thing is, a lot of our series are these fractions, right? And that's going to be true for ratio test as well. So instead of writing this, over this, what a lot of people do, even as their first line, they take the n plus 1, but then they just immediately flip this one and multiply. So that's an plus 1 divided by an, flip and multiply. All right. Now the hope is that a lot of things are going to cancel out, simplify really, really nicely. And so we've got to be kind of clever about canceling, but this one's going to cancel out really nicely for us. It's going to play right into our hand. For one, you notice the threes. Like, oh boy, could I cancel? Hey, 3 to the n plus 1. Isn't that 3 to the n times 3 to the first? When we probably don't really think of it that way, but if you were to multiply here, wouldn't you add the exponents? So if I break it up, then I can get this to cancel out really nicely. Okay. Let's look at n plus 1 factorial. And it turns out n plus 1 factorial is the same as n plus 1 times n factorial. Now, we haven't talked very much about factorials. They've popped their heads up, occasionally, seldomly in this chapter so far. They're going to be getting a little bit more common. So let's talk about this. Hey, n plus 1 factorial. Isn't that n plus 1 times n minus 1? And we would keep counting down. I seem to have left the screen. We would keep counting down until we got to 1. Well, hey, what is this right here? Isn't that n factorial, that whole thing? So n plus 1 factorial is n plus 1 times n factorial. Oh. Well, that's really, really nice, because then our n factorials are going to cancel out. So what are we going to have left? Well, not a whole lot. We'll keep the absolute value, 3 over n plus 1. We're taking the limit as n goes to infinity. Well, that's going to be 0. And once we get 0 here, we're thinking, okay, let's go back to how the ratio test was defined. Hopefully you wrote that down. If the answer to the limit of the absolute value of your ratio is less than 1, which I've noted, then what happens? And yep, it converges. Not only does it converge, but it converges absolutely. And we'll just go ahead and cite the test as well by the ratio test. And that's pretty slick. That's a pretty fast way to show absolute convergence. We're not surprised that these things cancel out so nicely, right? When we take that next term, if we ever use a ratio test, we're really looking for that really nice cancellation. Okay. Let's take a look at this one to finish off this video. Let's see. From 1 to infinity, 1 to infinity, 2 over n to the third plus 1. Okay. Let's apply ratio test here. All right. So an, right, I just copy it, but then the n plus 1 term, I'll replace the n with n plus 1. 2 over n plus 1 to the third plus 1, like so. And then we're going to take the limit of the ratio, throw in an absolute value. And again, we're going to put this one first. We're dividing it by that, so why don't I just flip and multiply right here. Sounds good. And then I'm going to cancel out whatever I can. Now this one, just the nature of these polynomials, right, we're not going to be able to cancel much there. I mean, we can cancel the 2's for sure, but then we're left with n to the third plus 1, and I went ahead and just multiplied all this out. since we're not going to be able to cancel, let's at least simplify it. N to the third plus 3n squared plus 3n, and then with that extra plus 1 gives us a plus 2 here. And okay, so hopefully that's not too fuzzy on the screen for you. And so we didn't get near the nice cancellation that we were hoping for, but you know, it is what it is. There we go. All right, well, hey, to tackle this limit, you might notice it's infinity over infinity. You might apply L'Hopital's rule here. If you do attempt L'Hopital's rule, you're going to have to do it more than once. In fact, you're going to have to do it 3 times to get it all the way. However, you might do this one by a different way. L'Hopital's rule is a great way. I mean, you need it 3 times, but it'll work out nicely. Or maybe you realize there is an algebraic way to approach this. One way that sometimes gets shown in Calc 1 is to divide. In a case like this where you've got polynomials, if you divide every single term by the largest power in the denominator. So if you divide everything by n to the third, every single one of these terms divided by n to the third, then you can get this limit a little bit faster. So I'll leave that to you to investigate. We can talk about it in the live meeting too. I'm just going to mention these 2 techniques. So you could do 3 L'Hopitals. That'd be fine. Or you can divide each term by n to the third. Whatever you do, this thing is going to work out to equal 1. So you know, you do need to show one of these 2 possibilities to get from here to here. I don't want people to say, oh, this is clearly 1 because n to the third, n to the third. There are other, because there might be other situations that are not as obvious, or you know, other things might be going on. I need to see that work in the middle. I'm going to skip showing either one of them, as you can see, and just say that it comes out to be 1 for our lecture purposes. Hey, what did the ratio test say if once we were done taking the limit, it equaled 1? What conclusion? Oh, ratio test is inconclusive if it equals 1. Oh no. Well, if it's inconclusive, then we haven't made any progress. We have no idea. Ratio test is not the way to go here. We need to try another test. Ratio test did not yield anything for us. So let's try something else. So we got to start from scratch. Here's the original one again. 2 over n to the third plus 1. You just think, what other test could we use? And, well, you can see my thinking already. But you just go through the list, right? So is it a geometric series? Well, definitely not. A, r to the n. No. We're not, you know, is it divergence test? What if we took the limit of the nth term? Well, that would go to 0. So divergence test is inconclusive. Is it, what was next? Telescoping. No, there's not going to be a telescoping series on that. Is it going to be an integral test? Maybe. Could we take that integral? You know what? Now that I think about it, no. I don't want to take that integral because of the plus 1. Oh, but you know what? The plus 1, I could compare and compare it and have a p-series. Okay. So I'm going to remove the plus 1. And if I do that, the denominator gets smaller, so the whole thing gets bigger. And then to really show being careful mathematically, right, I'm going to pull that 2 out. I'd be fine if you use a p-series on this, but just to be super clear for myself, I'm going to pull that 2 out, give myself 1 over n to the third. Okay, so I've made the series bigger, and now what's going to happen there? If p equals 3 in the p-series, what does that mean? Converge or diverge? Well, it's bigger than 0. So we want the P to be large. In the P series, it converges if he wants them to converge. And it's not, we kind of think that we want things to converge, but that's just kind of like a personality we put to these things. It's not really, it doesn't really matter. Okay, so, but I like things converge. Okay, so it does what we want. It converges, I guess, by the P series. And that is bigger than this. So we know this converges by the direct comparison test. And I think that's it. Yeah, that's what we were trying to show was this guy right here. So ratio test didn't work out for us, but a comparison and a p-series did. Hey, we might have seen this very problem back a few sections ago. But it really just good, it kind of lends itself to experimentation, right? Try one, didn't do anything. That doesn't mean you did anything wrong. Just try a different test, just keep working it. Okay. Up next is the ratio test. See you then.